Good morning, everybody, or whenever you're watching this video. It's currently 1 a.m., but I feel great because I fell asleep at like 7. So I'm ready to go for the day. All right, so we're talking about acid strength and the acid ionization constant, Ka. It's going to work a lot like equilibrium constant, but we'll get there when we get there. So in general, when we have an acid, and this should be a bit of a review from yesterday, we're going to write, and it's often written in this form where the H is out front, because remember the H is what makes an acid. Remember that the acid gives off the H plus to the other thing. So in this case, the acid gave off the H plus to this water, and that's why now this water has an extra hydrogen and an extra positive sign. And then we put whatever's left, the acid, over here. So if this is the acid, we call this thing the base. And again, it's essentially the acid just gives off the H plus, and the H plus goes over that guy. And what's left once we give off the H plus has to be an A negative. And we'll be writing it like this a lot. And just to remind you, if this is in equilibrium, this is the acid. This thing that accepted it over here will be the conjugate acid. And this will be the conjugate base. And that's just because the conjugate base can go over here and accept an H plus from this one, and the reaction can go the opposite direction. All right, so there are a few strong acids you were tasked to memorize. Just throwing this out here. This one is called diprotic. They pointed out because there happen to be 2 hydrogens. There are things that even have 3 hydrogens. They're not strong acids. Remember, these ones are the strong. For example, H3PO4 has 3 hydrogens on it, and this is phosphoric acid. And this is considered triprotic. I just wanted to introduce some vocabulary that we're going to be using throughout the class. All right, so anything that is not on this list that is an acid, in other words, it starts with an H and it's aqueous, there's not a strong acid, is a weak acid. So if you come across something that's not on this list and it's an acid, it's going to be weak. If it's not on this list and it's an acid, it's going to be weak. This one, is that on that list? The answer is no. It is therefore weak. All right, so let's discuss the difference between strong acids and weak acids. So, for example, when we went through some acid strength stuff yesterday, we talked about HF, and I showed you HI. Now, there's difference in terms of electronegativity. There's also difference in terms of size. So this is a really small atom that it's bound to, and iodide is much bigger, and that's why H is able to leave more easily. This is the strong one. And in fact, I'm going to start with discussing the strong one. And this over here is a weak acid, because HF starts with an H, and it's not on that list. That is how you know it's a weak. All right, so if I were to take some HI and put it in water, so I take some some hydroiodic acid, and I throw it in water, it's going to break apart into H plus and I minus ions. And it's going to do what we call fully ionize. It's going to fully break apart. The iodides will be nowhere near the hydrogen ions. All right, and we would write that in a reaction like this. HI breaks apart to H plus plus I minus. And sometimes you might want to write an H2O or something like that. And these would usually be aqueous. Not usually. These would always be aqueous. And that's how we would write it. All right, but let's go over here to this weak acid. If you were to take some hydrofluoric acid and throw it into water, it would break apart also into H plus and F minus, with one caveat. a lot of these will still stick together and not break apart. In other words, they won't dissociate or ionize. So another way we write that is HF. This is where the two-way arrow comes in. We draw one arrow showing that, hey, it breaks apart. But the other arrow going back the other way saying, but not always. All right, so we'll have some HF that are fully ionized, and we'll have some HF that are not. And that's the difference between a strong and a weak. Notice this weak has a double arrow, and the strong have a single arrow. All right, so let's talk about equilibrium a little bit. If you remember, in equilibrium, we have A plus B, let's say, is in equilibrium with C plus D, and we would say that the equilibrium constant is equal to products, C, D, over the reactants, A, B, right? In an acid, much like like we just had HF breaking apart into H plus and F minus, and an acid is very, very similar. So let's go ahead and write the equilibrium constant for this, even though I have it there. I would say K is equal to H plus times A minus all over HA in this situation. And that would be correct. And if you're doing it for an acid, we just put a little A there to represent the fact that this is equilibrium constant for an acid. You'll notice that these two things are equivalent to each other, and I kind of want to talk about why that is. If I add water over here to HA, you're going to break that's going to break apart into H3O plus. Remember, this one gives off an H plus, and we'll have A minus left over. Water would be a liquid, and all of these would be aqueous. Okay, so if we were to write the Ka for this one, or the Ka for that one, this one would give us that Ka, and that one would give us that Ka. And there is no difference. There's no difference. Whether or not we have water or not isn't a difference. We oftentimes say that these two things are the same. We call this hydronium. We might call it this one, we call it a hydrogen ion, but it's just a hydrogen ion that's attached to water, and they are very, very similar in terms of how we discuss them in acid-base chemistry, and it just depends on sometimes your textbook, and now even your textbook is like, they're interchangeable. We use them interchangeably. So when you see H3O plus, think H plus. When you see H plus, think H3O plus. They're essentially the same thing. They can do the same. They can provide us with the same information. Okay. So here we have a table of various different acids, and mainly the point of this table was to show you just some standard acids. If you go through and look, I think they're all weak acids, and this would be their reaction. It walks through how they break apart and give off their H plus. But we already talked about acid strength a little bit. For example, we looked at these two things, the chlorous acid and the hypochlorous acid, and we already discussed that if we have an H and an O bonded to a lot of electronegative things, it's going to be a stronger acid. So here we have an H and an O bonded to one electronegative thing. And up here we have an H and an O, and it's bonded to two electronegative things. So we should expect that this acid is stronger, and that's exactly what we find. Now remember, I'll go through this table a little better here. Remember that Ka, oh, my camera's falling. Okay, remember that Ka is products of reactants, right? So if we have a big Ka, what that's telling us is we have a stronger acid. So if we have a higher Ka, we have a stronger acid. It's giving off that H plus more. It's creating more products over. It's creating more products over here, and if it creates more products, that means that it's going to be stronger. So if we have a high Ka, we have a stronger acid. P, we'll talk about in a little bit, but this pKa is the negative log of the Ka. And what that does is it also helps us determine strength. The pKa is generally a lot closer to, for example, the pH that maybe that thing produces. So a decreased pKa means a stronger acid. So over here we have 0.011 as the Ka, as opposed to down here, we would have 9 zeros before that 49. So it'd be a very, very small number. And the pKa associated with this one is really small, but the pKa associated with that one is much bigger. That was 9.31. All right. Okay, so consider these two acids. All right, so we have HF and HClO. And it says which one's stronger. So essentially you just look at the Ka. Again, we know that each of these in water would break apart into H plus. This one would be H plus and F minus. And this one right here would be HClO breaking apart into H plus and ClO minus. Okay. It's telling you that if you were to write this in an equilibrium constant, products over reactants, it would be 2.9 times 10 to the negative 5, and this one would be 3.5 times 10 to the negative 4. That is why this one is stronger, because it is a bigger Ka. Larger Ka tells you there's more products. All right. Now this next one, I kind of wrote some stuff here, but I don't know if I like it, but let's do it. So it says write the equilibrium expression for this. So this is water, just water acting as an acid. So it's breaking apart, it's giving off H plus, it's giving off OH minus. And when water acts as an acid, we would write the equilibrium constant H plus times OH minus all over, wait, water is a liquid. Do we put liquids in here? We do not. So pretty much we just have H plus times OH minus. Well, an H plus times an OH minus is very special. It is what we call the equilibrium constant for water. So it has a set value, and that set value is down here, 1.0 times 10 to the negative 14. That's the equilibrium constant for water. And we'll be using that value, I'll just turn that into a box, a lot. Before I get there, I want to show you how you make this one, in case anybody was wondering. If you react two waters, and one acts as an acid, and one acts as a base, that's how you'll get one to give off an H plus. So let's say this one gave off an H plus to that one, and then you're left with OH minus. Then if you write the equilibrium constant, you get this. But again, these guys are the same. All right. So knowing the equilibrium constant value for water, this, by the way, you just memorize it. You're going to use it so much, you might as well just memorize it. All right, let's talk about how that works. Okay, so from the H3O plus concentration, we can calculate the OH minus concentration in a particular situation. So here it gives us various H3O pluses. We'll do one example of these, and I think I only did one, but I could do them all, I guess. I only did one, but I lied. Let's just do them all so you have the answers. So here we have H3O plus is equal to 7.5 times 10 to the negative 5, and we know that 1 times 10 to the negative 14. You don't even need that 1. 1 times anything is itself. So 10 to the negative 14 equals our H3O plus times our OH minus, right? In other words, we're solving for OH minus in all these situations. Our OH minus will always equal H3O plus. Our OH minus will always equal 10 to the negative 14 divided by our H3O plus concentration will equal our OH minus. All right, so let's go ahead and solve the first one. Knowing this, I'm just going to take 10 to the negative 14 and divide it by this number right here to get my answer for the first one. So 10 to the negative 14 divided by, don't forget to put in parentheses the denominator, which is 7.5 times 10 to the negative 5. And this first one, I get 1.3 times 10 to the negative 10. And the exponents, by the way, should always add up to about 14 or 15. So 10 plus 5 is 15. It's negative 15, I get that. But just a good check to make sure that you did everything right is that the exponents here and the exponents from the number you used should add up to close to 14. All right, in our next situation, let's move on to this one. We have 10 to the negative 14 divided by, in parentheses, 1.5 times 10 to the negative 9. And we get 6.7 times 10, and then we could just 1, 2, 3, 4, 5, 6 to the negative 6. And hopefully that makes sense because, again, they want to add up to about 14, 15. So 9 plus 6 is 15. Okay, and last but not least, 10 to the negative 14 divided by, in parentheses, 14 divided by, in parentheses, 10 to the negative 7. And I get 1, 2, 3, 4, 5, 6, 7. What a surprise. I get, you would do 1.0 times 10 to the negative 7. And again, make sure that those exponents add up. This would be what we call a neutral solution, when the amount of H3O plus is equal to the amount of OH minus over here. When these two things are equivalent, your solution is neutral. I have to write that. Okay, so what is pH? This is kind of a loaded question, and this is not how I meant to write this. But P of anything means negative log of. So the pH is the negative log of our H plus concentration, which, don't forget, we also call H plus H3O plus. That's what pH is. And what that does, when you look at concentration, if you have a really high concentration, your pH is going to be really low. Kind of like when we talked about the Kas and the pKas. So if you have something that's a really big number, the P of that number is going to be smaller. And all it does is it takes an exponential scale and puts it in terms of like a regular scale that we can manage a little better. So an example would be our pH scale. You'll find it even goes to negative values actually very soon, but is generally about 0 to 14. We're at 7. We call that neutral. And 0 to 7 is acidic, and 7 to 14 is alkaline or basic. So anything from 0 to 7 is going to be acidic. Anything from 7 to 14 is going to be alkaline. Anything as 7 is neutral. This would be our pH scale. Now I told you we're going to take exponents, like the concentrations, they're always 10 to the negative something, right? Or 10 to the, like a very small number. And then we're going to put them into a normal scale. Well, let's talk about how that works. Something like that, that's enough. All right, so this goes all the way down to 14, right? But let's say I have something that's here and here, and I want to know the difference in acidity. So one thing has a pH that's 1 and one thing has a pH of 3. Well, the difference between these two, I hope you agree, is 2. In other words, the real difference is actually 10 to the 2, the difference between 1 and 3. What if we go from a 1 to a 5? That's a difference of 10 to the 4 in terms of concentration. What about a 1 to a 7? That's a difference of 10 to the 6 in terms of concentration. What I mean by that is this one is 10 to the 6 times more concentrated than this one up here. So I'm going to say that again. If you have a solution with a pH of 1, that means it's 10 to the 6 times. That's a million times more concentrated than something with a 10 to the 7. And that's how a logarithmic scale works. All right, so now that we have a general understanding of a logarithmic scale, and we know what pH is and what P is, let's talk about POH. Remember, P is negative log of, so POH is just negative log of the OH minus concentration. What do you think pKa is? That's just negative log of the Ka. That's it. All right, some things to think about before we get too far into working with logs, etc. is just some housekeeping items. So if you take the negative log of something that has 2 sig figs, the resulting answer is going to have 2 decimal places. So if you take the log of something that has 2 sig figs, the resulting answer will have 2 decimal places. And so if you took the log of something that had 3 sig figs, the resulting answer would have 3 decimal places. And you'll probably get used to that. It actually almost comes intuitively. So for example, in this next problem, we're going to calculate the pH. We're going to take the log of it. This has 2 decimal places, and therefore our resulting answer should have, or this has 2, sig figs, so our resulting answer should have 2 decimal places. All right, let's go ahead and do it. So calculate the pH, boom. You see on H3O plus, your immediate response should be knowing that pH is equal to the negative log of the H plus concentration. In other words, the negative log of 1.8 times 10 to the negative 4. The beautiful thing about this, by the way, is these exponents help give us an idea of what the pH is going to be. This tells me it's going to be about 4. Sometimes it might end up about 5, but it's generally going to be really close to around 4. And so that's hopefully helpful in guessing these things. Okay, so it'll be anywhere plus or minus 1 of that value. All right, so negative log of 1.8 times 10 to the negative 4, close my thing, and I get an answer of 3.74. And it should make sense, again, because it's plus or minus 1 of that exponent. So 3.74 is the pH of this one. Let's move on to this next one. There are actually 2 different ways to solve this one. And we know them both now already. Get some paper. Okay, so we have our OH minus is equal to 1.3 times 10 to the negative 2. Okay, there are 2 ways to solve this. Way 1 is to find H3O plus and pH. Let's go ahead and let's go ahead and do that way first. All right, so to find H3O plus, remember we have Kw, which is equal to 10 to the negative 14, is equal to H3O plus times our OH minus. So we're given OH minus. We can solve for H3O plus by plugging in, chugging into this equation. And then we find out that H3O plus is equal to 10 to the negative 14 divided by, in parentheses, 1.3 times 10 to the negative 2. I think I screwed up, yeah, sorry, I can't see very well. So I'm gonna do that one more time. 10 to the negative 14 divided by 1.3 times 10 to the negative 2. And I get 7.69 times 10 to the negative 13. I ask if it makes sense. Do those two exponents add up to close to 14 or 15? They do. All right, so that's our H plus. And then we know that we can take the negative log of that answer to get our pH. And I get 12.11. Remember, we took the log of 1. This had 2 sig figs. This one had 2 sig figs. That had 2 sig figs. So we should have 2 decimal places right here. 12.11. Okay, so that was one way. Let's do the other way. This is the way that I tend to prefer, but it doesn't necessarily mean you're gonna prefer it. I'm not a fan of small numbers. So one of the first things you can do is get rid of that small number. So this way, we're gonna find POH and solve for H plus, or for pH. So again, we got our OH minus. Our POH is gonna be the negative log of the OH minus. I like getting that step out of the way right away. So you just say negative log of 1.3 times 10 to the negative 2. And I get an answer of 0.886. Now, one equation we really haven't gone over, but you could figure it out, is this one. pH plus POH equals 14. Remember that this is our POH, so we know pH plus 0.886 equals 14. So now just 14 minus our last answer. Oh no, I must have had a, no. Did I input the negative 1 up here? Maybe I put negative 3. It was fun. Okay, negative log of 1.3 times 10 to the negative 2. Oh, that's where I missed a 1. Okay, that makes a lot more sense. Okay, I'm sorry. Maybe you guys saw that, but I didn't. I have a camera in the way of my calculator in case you haven't figured that out. So then you do 14 minus 1.846. And you get 12.11. All right, so again, I just minus 1.886 in order to get 12.11. This is the way I prefer. Again, you get rid of that number right away, then you just subtract it from 14, and it becomes pretty straightforward. And you'll be doing it so much, maybe find the way that you're most comfortable with. If you like dividing it by using the 10 to the negative 14, and then taking the negative log of it from there, you do that, or this way. Both ways work, you'll get the same answer. Strong acids. So if you have a strong acid, so far we've been talking about weak acids with Kas. If you have a strong acid, it's the concentration of the acid that you put in there is going to be equal to the H2O plus concentration. And it's actually for the same exact reason we already talked about. So if you put in like let's say HI, right, the concentration of HI will be however much HI you add in there. It'll all break apart into H plus and I minus. In other words, whatever you put into the solution, it's going to go all the way and fully break apart into H plus and I minus. So let's say you put in 0.2, let's say you put in 0.2 molar. In fact, let's do a quick ice table. If you put in 0.2 molar, you're going to lose all 0.2 molar. These would have been initially 0 and 0. So if you put in 0.2 molar and you lost 0.2 molar, how much did you gain over here? Also plus 0.2 molar and plus 0.2 molar. And that way, at equilibrium, you have no more of this left because it fully dissociated. This is 0.2 molar. In fact, you could find the pH of this right now. What's the pH of 0.2? You just say, hey, negative log of 0.2. And you find out the pH of the solution just now that we just made up would be 0.699. Or 0.70 actually. All right, so anyways, I just thought that was kind of cool. So you can figure out the pH of a strong acid solution just by knowing how much you put in the solution. So here's another example. You've got 1.2 molar HCl. For that exact same reason, in fact, let's go ahead and do this again. If you put HCl in there, you know that's going to break it apart into H plus and Cl minus. If you put 1.2 mole per liter of HCl, you know at equilibrium you have 1.2 mole per liter of the H plus, right? So all we need to do to find pH, remember that's the negative log of the H plus concentration, which would be the negative log of 1.2. That's going to be a negative number. So negative log of 1.2. Is negative 0.08. Negative 0.08 would be our pH. This has 2 sig figs, so we should have 2 decimals here. All right, moving along. All right, but in weak acids, this is where we have the equilibrium stuff, and we're using Kas, etc. I'm gonna grab some water. Okay, so it says find the pH of a 0.100 mole per liter hydrocyanic acid solution, and it gives us the Ka. And it says assume X is small. We're always going to assume X is small, and it says Ka will always be given to you. All right. So we might look at this problem and be a little worried, but guess what? It is exactly the same as what we've already done and almost a little bit simpler than regular acid bases or regular equilibrium chemistry because there aren't squares, etc. It makes it pretty straightforward. So let's do this. We know if we got HCN and we put it in water, and this is how I usually like to do it. It's going to break apart into H plus and Cn minus. It tells us that the concentration was 0.1. What that means is that our initial concentration was 0.100. All right, but is HCN a strong acid? The answer is no. It's not on our list of things to memorize that are strong, so this does not apply for down here. All right, but we do know we're going to lose something, right? This is going to be 0.00, 0.00. We're going to lose some. We're going to call that X. If we lose X here, we know we have to gain X there, and we know we have to gain X there. So then at equilibrium, we have 0.100 minus X, X, and X. This is a very small Ka. What that tells us is very little of this is made. We don't get a ton of products. So when we go to plug this stuff in into our Ka, Again, it's the same as a K. We're just putting an A there to represent that it's an acid. We're gonna have H plus times CN minus all over HCN. If we go to plug and chug this into the equation, our H plus would be X. Our CN is X all over 0.100 minus X, which is coming from over here. Thankfully, it gives us our Ka. It tells us the number right there. It should always be given to you. Sometimes it's given to you on a table, and you're going to have to look at the table and figure it out. But now we're just going to solve for X. I'm going to simplify it down here a little bit. Maybe I'll get a piece of paper so I can write, so I'm not scrunching. Okay. So we have currently have 4.9 times 10 to the negative 10 is equal to an X times an X, which I hope you would agree is X squared, over 0.100 minus X. This, we said, is small. Compared to that 0.1, it's just a very small portion. It's a very small number. And it told us that we can make that assumption, which is very helpful. But again, we won't be doing quadratic equations, so you can always make that assumption in this class. All right, so let's go ahead and do this. 4.9 times 10 to the negative 10. And then I'm going to multiply times 0.100. I didn't need the zeros, but. And now we have 4.9 times 10 to the negative 11 equals X squared. And you're just going to take the square root of both sides to solve for X. So square root of the second answer, It tells me X is equal to 7 times 10 to the 1, 2, 3, 4, 5, 6, negative 6. And more specifically, 7.0. Cool. So X would be 7.0 times 10 to the negative 6, which I think is great. Definitely a very small number. Proves that if you subtracted it from 0.1, it wouldn't change anything. All right, so that's our X. But that wasn't even the question. I know I circled it. I was just excited to find X. But the question, always go back and look, it asked for the pH. Oh, man. Now we've got to bring in all our new stuff. But no worries, because remember, pH is just the negative log of the H plus concentration. What's our H plus concentration? Our H plus concentration is X. So this also equals our H plus concentration. To find the pH, all we do is take the negative log of the H plus concentration. In other words, the negative log of that 7.0 times 10 to the negative 6. So I'm just going to take the negative log of my answer that's still in there. And I get an answer of 5.15, which again should be plus or minus 1 of that exponent. And we know that that is correct. Yay, team. Okay, so in this case, the pH equaled 5.15. All right, so there's another example. This will be on the next page. Okay, a 0.100 mole per liter weak acid solution has a pH of 4.25, and it says find the Ka for this acid. All right, so we've got some weak acid. We don't know what it is, but we know its concentration, and we know its pH, and it wants us to find the Ka. All right, so one thing I maybe we should go over before we get to this problem. We've done a lot of pH. We know the pH equals negative log of the H plus concentration, right? That we know. Hopefully we're good with that. But if you want to go backwards, like let's say I give you pH and ask you to solve for H plus concentration. So for example, if the pH equals 4.2, and I'll say, what is the H plus concentration? What you do is you take 10 to both sides to get rid of that log, and that you still have that negative sign, so you end up getting 10 to the negative pH. It's just easier just to write it. So 10 to the negative pH is going to give us our H plus concentration. In other words, 10 to the negative 4.2 would give us our H plus concentration. In this case, it would be 6.3 times 10 to the 5. 6.31 times 10 to the negative 5. Which is pretty cool, right? So we can kind of go back and forth in each situation. And anytime you have pH, you can find H plus. Anytime you have H plus, you can find the pH. And this is how you do it. So this you might want to just memorize. All right. So back to this guy. So it says you got a weak acid, solute HA that has a pH of this. Find the Ka for the acid. Okay, so we have some HA. It's weak, so we got the double arrows. It's breaking down into H plus and A minus. We know that its initial concentration is the concentration of the acid itself. That. We don't know a lot, but if you want to start by doing X's, you're going to have to stop yourself because we do have some extra information. It tells us our pH is 4.25. If our pH is 4.25, that means we can find our H plus concentration. That's going to be 10 to the negative 4.25. So that means right here at equilibrium, we can actually find this. We can do the zeros. I like to do those. You know that. So 10 to the negative 4.25 gives us an answer of 5.62. 5.6. Really, you just have two sig figs. 5.62 times 10 to the 1, 2, 3, 4, 5. -5. So at equilibrium, we've got 5.6 times 10 to the negative 5 is our H plus concentration. It doesn't hurt to keep that extra 2, but really it would only have two sig figs at this point because this had 2 decimals. So, all right, so we got 5.62 times 10 to the negative 5 is there, which means we had to have gained 5.62 times 10 to the negative 5. If we gained 5.62 times 10 to the negative 5 there, it means we also had to gain 5.62 times 10 to the negative 5 there. And how much did we have to lose here? Oh yeah, we had to have lost 5.62 times 10 to the negative 5. This is very small compared to that 1.1. Really, this 0.1 still ends up being 0.100. You could subtract it off, but you'll sig fig wise just look at the same answer. And this is 5.62 times 10 to the negative 5. So now when we're plugging in our Ka, it's our A minus times our H plus all over HA. In other words, 5.62 times 10 to the negative 5 times another 5.62 times 10 to the negative 5. In other words, this times that would be that squared all over 0.100. All right, I'm going to take this answer, I'm going to square it, and I'm going to divide it by 0.1. I get an answer of 3.2 times 10. I think that's an 8. 1, 2, 3, 4, 5, 6, 7, 8 times 10. So negative 8 is going to be our Ka. All right. So I've shown you where we have Ka and we can solve for the concentration. We can solve for the pH. Now we have where we can, given the pH, and you have to solve for a Ka, and walk all the way through those. So, great job. Okay. Now we're moving on to acids. So memorize these strong acids. Boy, this didn't come out very well. This one right here is SrOH2, strontium hydroxide. So we have lithium hydroxide, sodium hydroxide, potassium hydroxide. Notice these are all in the first column. The lithium, sodium, and potassium in the first column on the periodic table. These guys are in the second column on the periodic table. When we pair them with a hydroxide, it makes what we call a strong base. So just like I had you memorize your strong acids, you're going to memorize these. Generally, if it's got an OH minus, it's going to be strong, but there are some situations where they're weak. For example, aluminum hydroxide is weak. So just memorize these if you can. That would be really, really helpful. Then we have some weak bases over here. Similar to the weak acids. And what these do is they will accept NH plus, but not a whole bunch. Just like a weak acid will give off NH plus, but not very well. Same thing with OH minus. By the way, these things with OH minus, strong bases will always accept NH plus. Actually, they just give off OH minus really, really well. All right, so we'll get into it a little more here with some examples instead of talking. So let's start here. What are the concentrations in pH in each solution? Okay, so these happen to be both strong bases. And just like with a strong acid, if you have a strong base, you can solve for the pH like right away. You don't need to do a table, a nice table or anything like that. So for example, here we have 0.225 is our KOH. And remember, strong base, if you put it in solution, or I don't know why I drew a negative sign there, I was already thinking ahead, breaks apart into K plus and OH minus. It's a single arrow because it's strong bases will fully dissociate. Well, we already know if this thing completely breaks apart, then whatever concentration this was has to be the same concentration of this thing at equilibrium. In other words, or once the reaction's gone to completion. In other words, this is our OH minus concentration. All right, this 0.225 is our OH minus concentration. We know how to solve for pH once we have an OH minus concentration, right? There's those two different methods. My favorite one is to first find the POH, and that's just the negative log of that 0.225. And then I'm going to subtract 14, or subtract it from 14. But first, negative log 0.225 gives us an answer of 0.648. All right, and now once we have that, we say, remember our pH plus POH equals 14. In other words, our pH is going to equal 14 minus the POH, which is 14 minus 0.648. So I usually just do it that way and then take the absolute value. So 13.3. 5.2 is what I end up getting. Okay. I'm gonna check just because I got a different answer than mine, so I want to make sure that I did it right. Negative log and didn't type something in wrong. 0.225 minus 14. 13.352. Great. I'm good. Good with that. All right. So moving on to the next problem. Same exact situation, but now Remember, this broke off into a K and OH minus. Let's look at this next problem where we have, I'll write it here so then I can get rid of this paper up here. We want to know what the pH is when we have strontium hydroxide, specifically 0.015 molar. All right, let's talk about strontium hydroxide. You should see a difference between potassium hydroxide up here and strontium hydroxide. The difference being this has two hydroxides. So when you put strontium hydroxide in water, it's going to break apart into strontium plus 2 OH minuses. So if we were to do our ice table, if we start with 0.0015 here. Now remember, this is a strong base, so everything's going to react. We're going to lose 0.0015. These start at 0. If we lost 0.0015, how much did we gain here? Hopefully you're saying plus 0.0015. And how much did we gain here? Don't forget there's a 2 there. In other words, we gain 2 times that amount, 0.0030. So at an equilibrium, this is 0, this is 0.0015, and this is 0.0030. So our OH minus concentration at equilibrium, or after the reaction's gone to completion, is 0.0030 molar. So from there, now we can solve for the pH, which is what the question asked. So this is our OH minus concentration. Now we can find the pH. Remember, I like to say negative log of 0.0030. That's going to be our pOH. And that comes out to 2.523. Seems pretty. It's pretty high to me. All right, negative log. Okay, I'm going with it. All right, and then we just say 14 minus that answer. This is a small concentration. Gives us an answer of 11.48. All right. Cool. So hopefully, so our answer is still, it's alkaline. It makes some sense. Both of these, right, are bases, so we should expect that their pHs be above 7, especially for these strong bases. I am a little bit surprised that this is so low, but not really, because it is a very low concentration. So I changed my mind as I'm thinking through it. All right, let's move on to the next one. Okay, here it says find the OH minus and the pH of a 0.10 NH3 solution, and it gives us the KB. Okay, so here, these were strong bases, right? Now all of a sudden we're given a KB. What that means is this is a weak base. So very similar to the weak acids, we're going to create an ice table, etc., and solve for X. It says assume X is small, so that's awesome. All right, so first let's talk about what would happen. Anytime you have a weak base, you're going to react it with water to make your ice table. It's going to make it a lot easier, I think, because then water can act as the acid, and you can see what happens. So when water acts as an acid, it gives off an H+, right? So then we're left with NH4+. plus OH minus. So whenever you have a weak base, you're going to be looking to see that you can get OH minus, because that's going to help you determine the pH and all this other stuff for these problems. All right, we've got our ice table. Our initial concentration of NH3 is 0.100. We don't care about water, it's liquid. These guys are 0, and these guys are 0. We're going to lose some amount here. We're going to gain some amount here, gain some amount here. And then the equilibrium, it's 0.100 minus x, x, and x. All right, so our Kb, which is our equilibrium constant for our base, is just NH4 plus times OH minus all over NH3. Where we plug these numbers in, x, x, and that. So we have x times x is x squared over 0.100 minus x. It tells us to assume x is small, so we'll just get rid of it. It's going to be very small comparatively. And what was the Kb? 10 to the negative 5. Yeah, it's kind of pushing it. It's right there. All right, and now we're just solving for x. So we know our Kb is 1.76 times 10 to the negative 5, right? So we're going to multiply times 0.100. So now we have x squared equals 1.76 times 10 to the negative 6. And then we'll take the square root of that. So I'll just do it. 2, 5. Oops. And we'll take this circle. All right, and I get an answer of x, square root of both sides, by the way, is equal to 0.00133. All right, but what is x? X is our OH minus concentration. It's also our NH4 plus concentration. But the question asked to find the OH minus concentration and the pH. Okay, so this is our OH minus. We're done with that part. Yay! But now it asks for the pH. Let's first find the pOH, which is the negative log of that. So I'm just going to take the negative log of this answer, and I get 2.8. 2.88. We were keeping some extra sig figs here, by the way, that only technically had 2, 3. This had 3. Just kidding. That has 3. That has 3. So it should be 2.8. I'm glad I'm catching this. 2.877. And last but not least, it wants us to find the pH. So pH plus pOH equals 14. pH plus 2.877 equals 14. And I'm just doing 14 minus 2.877. And I like to keep all my extra sig figs. It is 11.123. Oh, that was fun. All right, and that would be our pH. So we had our OH minus concentration here, and we have our pH here. So it was kind of a two-part question. All right, so hopefully you're kind of seeing that there's some similarities between the weak acids and the weak bases, right? We set them up very similarly. The only difference is the weak acids we solved for H plus and then found the pH, and weak bases we solved for OH minus and then find the pH. Oh yeah. Okay, we're getting there. Yeah. All right, so we're going to talk about salts. Before I get to the problem, let's do an example. And I just took a break, by the way, to grab some coffee and put my watch on so you didn't have to see my weird watch tan line anymore. So, so some acid-base properties of salts. So like if you have a strong acid, like HNO3. When we put this in water, it breaks down into H plus and NO3 minus. Another aspect of the one-way arrow, in fact, actually one of the main things that we actually don't talk about, even though maybe we should, is that this is now it can't go the other way. We've broken this apart completely. And the whole reason we broke it apart is actually not the H plus, it's because of that NO3 minus. That NO3 minus doesn't want to go back the other way. So for all strong acids, when you break them apart, they don't want to go back the opposite direction, right? And that's because we call this neutral. It has no base properties. It can't become a base and accept that H plus and go the opposite direction. That salt is neutral. All right, let's compare that to like HF. This is not a strong acid, right? This is a weak acid. And when we break it apart in water, it's going to break out into H plus and the F minus, but we know it goes back. Most of the reason it actually goes back is because this guy is a decent base. Remember, we would call it its conjugate base, but it's a base, and it can go back in the opposite direction. And so if we're measuring the pH of, like, if we have some F minus and we're measuring its pH, it's actually going to be slightly basic. All right, let's keep going. So these things are what we would call salt. They're not the full salt, but they're salt ions. Let me be careful about that. Okay, anytime we have an anion, you can ask if it's going to be a weak base or not. So let's do an example. So the examples we have here, we have NO3 minus, NO2 minus, and C2H3O2 minus. Okay, they are going to be neutral if and only if they came from a strong acid like this. This one came from a strong acid, therefore this one is going to be neutral. As opposed to this NO2, HNO2, this is strong or weak. Hopefully you're shouting that it's weak because it's not on our list of 6 things to memorize. So this would break down into H plus and NO2 minus, NO2 minus, therefore must be a weak base. Here we have acetate, an acetate ion, C2H3O2, H, C2H3O2, acetic acid, aka vinegar, would break down into H plus and C2H3O2 minus. You don't really need to do any of this that I'm doing. All you have to do is recognize that if you add an H to that, it wouldn't be on your list of strong acids. And because of that, this can go in the opposite direction. This can be a weak base, and that's why this is a weak base. All right. The same thing can happen with strong acids, or excuse me, with bases. So, I'm running out of paper. That never happens. Anyways, so for example, like if you have a strong base like NaOH, we know that it breaks down fully into Na plus and OH minus. It can't go back the opposite direction. And so now we're looking at the cations. That would be a neutral. It can't act as an acid. But if you have a weak base, I got an example, like aluminum hydroxide. This would actually do this, because it's not on your list of strong bases to memorize, right? It would break apart into aluminum and 3 hydroxides. But more importantly, this, because it's a double arrow, could act as a weak acid. And accept that OH minus and go the opposite direction. All right, I'm realizing that that might freak you out, but metal ions can act as weak acids. Okay. And I can give you, I'm trying to think of how I can give you an example of how. So I'll show you how just real quick, in case you're wondering. So if I put aluminum in this, remember water is H plus and OH minus. That positive charge can pull the OH minus towards it. And in fact, you'd have 3 of them, and you'd get aluminum hydroxide. So the aluminum takes on the OH minus, leaving H plus in solution. And by definition, an acid is something that gives off H plus, right? So that's kind of how that works. But the main thing to pay attention to, strong base is going to give neutral ions, and a weak base is going to give slightly acidic ions. All right, now let's look at salts. Salts are when you put 2 different kinds of ions together. Maybe before I get there, I'll give you an example. If you have a strong acid, H, Cl plus NaOH, a strong acid and a strong base, and you react them together, H plus, this guy's giving off an H plus to that OH minus. What you're going to get is water. That goes over there. And whatever's left, NaCl. Because it's strong and strong, this is going to be a totally neutral salt. And we call it a salt when you have an ionic compound that's made from the leftovers of some acid and some base mixing together. So let's use that information and see if we can figure out, use all of that information we just went over, and see if we can figure out the answers to these. All right, so I'm gonna go through each of these and break them down. So the first one is strontium chloride. In other words, we're looking at strontium and chloride ions. Our question is, are the positive ones left over from a strong or weak base? And are the negative ones left over from a strong or weak acid? So strontium is left over from a strong base. Remember, strontium comes from strontium hydroxide. So this is comes from a strong base. Because it comes from a strong base, that means it's neutral. This came from SROH2. This one came from HCl. Because it's left over from a strong acid, it is also neutral. Aluminum bromide. Let's look at these individually. Let's look at the aluminum and the bromide. The first thing I see is bromide. I know that HBr is a strong acid, so this guy must be neutral. Oh, by the way, this whole thing, you just look at both of them and see which one's stronger. Together, they're both neutral, so this whole salt will be neutral. All right, so over here we have bromide, which is neutral, and we have this. This is coming from aluminum hydroxide. Remember, aluminum hydroxide is a weak base. If we have the remnants of a weak base, what that means is that this is going to act slightly acidic. So overall, this is going to be acidic. If you take aluminum bromide and you put it in water, it'll actually act as a weak acid. We've got this methylamine thing. NO3. Hopefully you recognize that this part is the nitrate and this is separate from it. So it would break down and this methylamide, or methyl ion, let's see, and NO3 minus, or nitrate. This, hopefully you recognize, is the remnants of HNO3, so this would be neutral. HNO3 is a strong acid. This, hopefully you don't recognize it too much at all. I don't either, but it's a positive charge thing, which tells me that it can be acidic, and it's not a positive charge thing that's left over from a strong base. I know that this is not part of a strong base, and therefore it is acidic. So overall, this whole thing's acidic. Next we have nacho. All right, this would break down into Na+, which I reckon, well, let's stay consistent here. And this guy, I recognize Na+ is from NaOH, which was one of the strong bases we had to memorize. This is therefore neutral. Again, it's because it comes from NaOH. That was a strong base. This, on the other hand, is not from any strong acid that I recognize, and that makes this a weak base, or basic. So overall, we got a neutral and a basic. The overall thing must be basic. nachos are not basic. Not in my opinion. And then we have NH4, F. This would be NH4 plus. And this would be F minus. And now we might be in some trouble because when I look at this, I'm like, oh no, wait a second. This is the remnants from a weak base, so I know that this is acidic. And this is from HF, and HF is a weak acid, so I know that this must be basic. So which one's which? But that's okay. That's when we're gonna look at you could look at the Ka and solve for the Kb of one of them, or you could just look at a table. I'm just going to tell you. So the Ka of NH4 plus for this one is 5.68 times 10 to the negative 10. I want to see if that Ka is stronger than the Kb. The Kb of this one is 1.5 times 10 to the negative 11. So which one's stronger? The acid side or the base side? Hopefully you agree the acid side because it's got a larger number. And that's why that's going to win. And this is going to be acidic. So if you come across this situation, you'd always be given these, and you'd have to determine which one is going to win. So if you took ammonium fluoride and you put it into water, it would be slightly acidic, ever so slightly acidic, because it's competing with that base as well. Is that everything? All right, beautiful class. I think that is everything. So have a great, great day, and I will see you in class.